right, welcome to the stage, Hamish Mackenzie, the moderator for this session.
Thanks very much, Lucian. Good morning, good afternoon, or good evening, depending on where you are in the world. My name's Hamish Mackenzie, and thank you for joining us for this IIoT World Energy Day session, which is called Seconds Matter, Real-Time Decisions for Smarter Energy Systems, sponsored today by CrateDB. Before we get started, it'd be great if you can tell us a bit about who you are, where you are in the chat. Always nice to get a feel for who's joining us. And while you do that, grab a coffee, whatever you need to do. Just a couple of points of housekeeping from my side. I'm sure most of you know, the session's going to last an hour. We're going to be introducing the topic and the speakers. We're going to be getting a lot of insights from them, of course, but hopefully, cross fingers, we're going to have time at the end, about 10 minutes or so to get your questions as well, to answer your questions rather. So it's always tricky because there's always lots to discuss, but we always do our best to do that. So please, if you have a question, get it into the Q&A section in the tool. Don't use the chat because it just makes it a lot harder for us to find the question. So if you've got a question, put it in the Q&A tool, and we'll get to as many as we can at the end of the session. And we hope we get to yours as well. If we don't, then we will make sure that your question gets answered after the session as well. Don't wait till the end. As soon as you have a question pop up into your head, get it in there into the Q&A tool, and we'll do our best to answer it. All right, so let's focus on the session. Our topic today is the transformative role of real-time analytics in energy operations. And that includes, of course, grid optimization and renewable energy integration as well. And as the energy sector increasingly operates on tight timelines, delays are critical in terms of if you have them, they lead to inefficiencies, instability, and so real time is something which is becoming increasingly important, especially low latency decision making in maintaining system stability and driving operational efficiency as well. And we're going to be getting some insights into some of the tools and techniques that can be used to deliver those split-second analytics that the energy sector now needs, and enabling smarter and more adaptive energy operations to address the challenges of this rapidly evolving industry. So that's the topic, and I'd like to now introduce our very special guest that we have with us today. First up, we have Simon Prickett, who's Senior Product Evangelist at CrateDB. He's very experienced in developer relations, systems architecture, technical training, and he's specialized in mobile applications and IoT specifically. He's led development of an IoT platform enabling buildings to participate in demand response energy markets. He's a hands-on full-stack developer in multiple languages and frameworks, former practice lead at Modus, contributing to complex mobile applications. And he's passionate about multiple things, including IoT, Raspberry Pi, supply chain logistics, and last mile delivery optimization. So very pleased to have you with us, Simon. Next, we have Zainab Gilani, who is Research Associate at Energy and Power at Cleantech Group. And Cleantech Group is a research company engaging with innovators and investors to generate insights on market trends across various cleantech industries. She's specialized in emerging innovations, technologies, trends with a focus on grid technology, nuclear energy innovation, and long-duration energy storage systems. She has experience in evaluating markets and investment dynamics in this space, and that includes understanding impacts on the energy landscape from data centers. And obviously, data centers, huge topic in all sorts of areas at the moment. Great to have you with us, Zainab. Next up, we have Anne Duncan, who is former CIO at the US Department of Energy, where she led IT modernization and cybersecurity initiatives. She held leadership roles also at Dell Technologies, US Environmental Protection Agency, and the County of Santa Clara. She has extensive private sector experience also at Hewlett-Packard. She's a very experienced published author, frequent speaker on topics like digital transformation, government technology, and organizational strategy. And she's been recognized with numerous industry awards, including Forbes CIO Next 2024 and multiple FedScoop honors as well. So thanks very much for joining us, Anne. Next up, we have Jürgen Suterletti, who's Vice President, Energy Segment Data Analytics and Marketing at Gantner Instruments. He leads that company's focus on edge computing and cloud-based energy asset monitoring. He drives the development of GI Cloud, a high-performance data backend integrating analytics and visualization tool. And he specializes in data-driven decision-making, machine learning-based modeling, and cost-efficient energy solutions. He's extremely experienced in power electronics, systems engineering, and entrepreneurship as well, with a focus on scalable energy solutions. So thank you very much for being with us as well, Jürgen. And last, and very definitely least, a couple of words about me. I'm the moderator. My name is Hamish Mackenzie. I'm a former IDC analyst, and I've been running my consulting, advisory, and coaching service from Munich, Germany since 2006. My focus is on helping small and medium-sized industrial technology vendors increase their growth efficiency. And I work with them on various areas: sales, marketing, customer success, recruitment and productivity, various aspects of the go-to-market strategy, essentially. If you'd like to know more about me, please look me up on LinkedIn. I'm pretty sure I'm the only Hamish Mackenzie in Munich, so it shouldn't be too hard to find me. With that, quick reminder, please get your questions into the Q&A. We'll get to as many as we can by the end of the session. All right, so let's get into it. I like to start these sessions by kind of setting the scene, giving people some context. So if I can come to you first, Simon, what is your take on the global energy sector overall in terms of the role real-time data plays within the industry right now?
Okay, so first up, I'm a database product person, so I'm not working in the industry at the minute, but because I work in real-time analytics, we are seeing a lot of interest from the industry. And as you said in the introduction, I sort of have a interest in this with building IoT stuff, and I used to work on a couple of demand response projects. With that said, and I think it's a little bit of a cliche, but obviously there is a lot of transformation going on at the minute, and I think that can be sort of divided into, for what I'm seeing from where I sit, the sorts of energy sources. So there's an increased and more urgent move to renewables, but there's also a sort of focus on sustainability, and some of the things that enable that sustainability. So, for example, if you think of all of the AI stuff that people are putting into energy and other industries at the minute, that can help with a lot of demand prediction and helping to save load and make things more efficient. But it itself also uses a lot of power, both in data centers and databases and models and storing data. Mm-hmm. And then the other thing that I see with, you see a lot of devices behind me that are essentially little IoT displays. They mostly have Raspberry Pi Picos in there. I'm a consumer, you're a consumer, we're all consumers of energy. And the tools are now available to either the more technical consumer, but also the sort of less technical consumer to look at their usage in more detail than ever before and monitor it. So I have a couple of plugs that cost next to nothing, and they'll tell me, how much draw is coming from that device. And then I could maybe do something about it and work with supplier API and data and so forth to figure out when's a good time to, I don't know, charge up an electric bicycle or something. So I see consumers being quite a big driving force in this, especially with things like, changing over to, we're all going to be changing to electric cars. But here in the UK, a big thing at the minute is we heat our houses because it's cold here in winter. We mostly do that with natural gas boilers. And there's a big shift to electric heat pumps, with which generally comes a lot more instrumentation and devices and so on. And then what do I see real-time data? What's the role of that? Generally, I think it's been seen as a sort of monitoring and billing thing, maybe for energy trading markets. But again, now it's like consumers actually want real-time data and they want it very granular. And they will change supplier to get this. We have suppliers over here who provide a lot more data than others. And they attract not just the technical customer, but other people that are just interested in that sort of thing. Mm-hmm. And I think for moving to renewables, real-time data is key in optimizing both the generation and new things to the grid, such as battery storage. And generally, I just see that obviously real-time is getting, by real-time we generally mean not near real-time. It's getting more and more closer to real-time, with more and more data taking part in that decision, and that's something we'll dig into further in the session. So I think that's enough for me. I'll hand this over to the next.
No, that's great. No, that really sets the scene well. So thanks very much for that, Simon. If I can come to you next, Anne. I mean, you must have seen a lot of stuff in your time at the Department of Energy. Maybe you can tell us a little bit about some of the infrastructure modeling that the Department of Energy does and how that enables real-time grid management over there in the US.
Sure, Hamish, happy to do that. I think I'd probably divide it into sort of 4 types of models. So first of all, there are models that look at capacity overall and what happens when we add and subtract from the grid. And these are really big, generally speaking, models that are very large. modeling either the entire U.S. national grid or significant segments of the grid, or even the interactions. We obviously have a lot of interactions with the Canadian grid, and so we have interactions there that are modeled as well. So those are big models that look at everything that's on the grid. What happens when you say put some new renewables on, take some traditional service off, have outages, that sort of thing. So big capacity models. Mm-hmm. The second models that we see are models that are designed to determine the best places to site resources, right? So those are not as much about grid operations as much as they are about how do we maximize the resources that come onto the grid. The third type of model we see are models really about that are about planning and risk mitigation. So what choices do we make that will say harden the grid? We've looked at these models and we say, if we harden these 3 or 4 things out of 500 assets, we can reduce our risk of outages due to fire, for example. And then from there, we go to sort of almost near real-time models that say, we do have a fire or we do have another issue. When do we take things off the grid? Or more importantly, a windstorm that might generate a fire. When do we pull things off the grid to reduce the risk of that causing a fire? Mm-hmm. And then finally, the most interesting thing from the standpoint of this group are those real-time operations. For example, models that look at, we've got a wind farm, and when the wind shifts 3 degrees, right, how do we readjust each wind turbine to maximize the capacity from the wind turbines, because each wind turbine interacts with the others in the farm. So as the wind shifts, you may slow one down, you may speed it up, you may stop one entirely. And that allows you to maximize your power. And similar things, obviously, some of these models we built are used by the grid operators within DOE as well to understand how to change their mix of power at any given time. Some of that is obviously to the point. It's a model that is then providing automated outputs that says that actually interfaces to the control systems and does those things automatically up to a certain point before an operator intervenes. So trying to predict, so we see these changes, let's go ahead and make these proactive changes into our operations that will then keep the grid up and running and reduce costs and maximize efficiency. So those are sort of the series of models that happen at DOE, everything from the planning to those real-time implementation models.
Okay, great. And obviously in terms of things like weather events, which seem to be getting more unpredictable, then that makes this whole aspect even more important, I guess. All right, thank you very much for that. Simon mentioned, I think I mentioned it as well in the intro, data centers. And so I wanted to come across to Zainab now. Zainab, the growth of data centers has obviously been top of mind for a lot of reasons, not necessarily energy related, but in terms of AI, for example, generally. How can innovation be used to support those data centers and grid operators when it comes to managing large energy loads, which only seem to be getting bigger?
Yeah, and it's definitely been coming up quite a lot. So this is a really interesting topic, and it's something that my colleagues and I at Clean Tech Group spend a lot of time researching. And I kind of want to start off with 2 main points. One is that, as I'm sure many individuals know, AI will require a lot of energy. So there are reports from Goldman Sachs that essentially state, different statistics like how a single ChatGPT search can potentially use up to 10 times more electricity than a standard Google search. And there are a number of different forecasts out there trying to predict how much energy exactly data centers will use. But I don't think we have to get too in detail into that. I think it would be a little bit more interesting to talk a little bit about how data centers can also help potentially scale other grid technologies as well. Technologies that can be used both for data centers and for the grid. And what's interesting when we're thinking about data centers is we're working a lot with quite a few, tech providers who are looking to scale as quickly as possible. And throughout this process, they might be willing to either take on a premium when it comes to energy prices, or they might be willing to invest in certain technologies that maybe other companies or utilities may not be as interested in investing in at the moment. So there are a range of different technologies that could be appropriate and applicable to data centers. These include things like batteries, battery management, different transmission equipment, virtual power plants, energy pricing tools. There's quite a large range. But I think, for the purposes of this conversation, it might be helpful to just give one example. Mm-hmm. And so I think one type of technology that I'm really interested in at the moment are smart transformers. So when we're thinking about, traditional transformers, those normally step up or step down voltage, and they're kind of passive. So there's not a lot of control or monitoring associated with those, standard technologies. But with smart transformers, you can incorporate real-time monitoring and analytics to better control and optimize these systems. And this is, really important for data centers because you're working with very sensitive, very expensive equipment. So if you have the ability to acutely, control power, voltage, frequency, it just helps support the longevity of those assets. So that's really important. And it's interesting to kind of see how different companies are trying to work potentially alongside with data centers to scale these technologies for the applications in the tech industry, but to also potentially scale these with grid operators down the road, or if they're not partnering with grid operators already, because as essentially we think about how renewables get connected to the grid, there's going to be variable outputs, and so you're still going to need better control and monitoring. So there's potential for these technologies to commercialize and then expand with the grid operators and utilities themselves.
Okay, fantastic. Thank you very much for that example, Zainab. So I want to ask Jürgen now, what is your perspective? I think a lot of people are a bit unsure about in all this in this topic, what should be done on the edge versus what should be done in the cloud, and where is that intersect between those two? Can you perhaps talk a little bit about that, please?
Yeah, for sure. When we have covered data centers, smart transformers, renewable energy generation, and I think depending on the task and on the feature what you need, you should do it on the edge or on the cloud.
Mm-hmm.
And another aspect is also the speed of response. How fast can I react to that? So if you have, let's say, local tracker control, local power plant curtailment, and so on, this has to be done immediately on the edge from controller. You would take real-time Linux systems for that and so on, so that you can immediately react to that without having any dependency on the internet. This is also usable for zero feed-in, where you have hybrid power plant with batteries and so on, or tracker control. So they should know for the next minutes or so what to do.
Mm-hmm.
So we can say closed loop, that should be there. But on the other side, also when it is really sensitive, we have a lot of online data analytics there, like fast Fourier transformations, which are done on the data streams immediately, which I think is also good locally to find out any safety things and so on, to put alarms on that. So this is also good when you have that ability to do it on the edge and not just do it post-processing on the cloud.
Yeah. Okay.
What's helpful?
I think you also want to just show a couple of slides in this next section, right? So yeah. Paul, could you bring up the slides, please?
Exactly. We have, I think, one picture with the backend one. This number 3 prepared. On the backend, I want to show you that. This is exactly a good example. So we talked about, what should go on the assets, on the edge and so on. But then you also need reliable, let's say also real-time data streaming to the cloud. And this has to be, not your proprietary protocol. That should be industrial standardized things, so that you can really use protocols which are, supported according to the specification, to the standards and so on. This is like Modbus, Ethercat, OPC, OA, and so on. That helps a lot. And once you have all the data in the cloud, we have here 4 important things. You always store the data in an event sourcing platform. We use here Apache Kafka, which is our persistent block and helps us to do real-time enrichment. So for example, if you want to aggregate the power from asset 1 to asset 2, this is done for each timestamp, even down to microseconds. And then we have a database like CrateDB, which is quite powerful for fast response, which helps us for indexing and aggregations. And this is then able to visualize, of course. We have our front end on that, where you can operate, analyze, and do the setups. But on the top right, you see that we can also run here MATLAB, Python code to train the models. And once the models are trained based on that raw data, really how they come in, we can then later on, with bidirectional communication, put the the function down into the controller and operate there standalone, so that we can come back to the first edge operational mode. And with this, you can really step-by-step improve. And that helps you to really optimize asset per asset. But also on the cloud, you can then really do with the hierarchies, with the asset combinations, the overall view, and get your reporting done and all that stuff. So this helps. And one last thing, what I want to manage, you have to be able that you can also send signals down to the edge. You can switch something off and so on. So that's quite important. These are my points.
Okay, perfect. Thank you. So I think we've got a good, we've set the scene pretty well there. And I want to move on now to talk about some of the challenges where, real-time analytics, monitoring, automation. Zainab, can you talk a little bit to that in terms of what are the challenges today that you see in those areas in terms of improving grid reliability specifically?
Yeah, and I think, it's quite a broad range. So I'm going to try and keep it simple. I would say maybe first, energy is kind of needed throughout the country. So when I was talking a little bit earlier about data centers, there's always going to be hot pockets where energy is needed. And trying to get it where it is needed most will be a challenge, especially as we're thinking about how different types of transmission infrastructure assets are aging. On top of that, it also takes a while to build out new transmission lines and additional infrastructure to do that. So I think one big question is, how do you make the most out of the infrastructure that you already have that exists today? And I think that gets into a lot of the optimization technologies that we're talking about. Another one is just avoiding power outages altogether and reducing the time back to power. Climate and weather-related events are going to be a huge challenge moving forward. There are different statistics out there, but one really important statistic from Climate Central essentially stated that between 2000 and 2023, around 80% of power outages were due to weather-related incidents, and quite a lot of those outages were in the latter half of the decade. So moving forward, we'll probably see quite a lot more challenges due to the weather. And then on top of that, it's kind of been mentioned throughout, but as we integrate more renewables and this kind of growing trend of electrification, whether that's homes being electrified, EV charging, we're going to see quite a bit of variability in energy and electricity through the grid itself. So understanding what kind of technologies are going to be needed to help stabilize that. So there are a range of different challenges, but I'm sure the other panelists will get into them a little bit more specifically.
Yeah, perfect. I'm very glad to hear that weather is mostly to blame, because normally it's my son that has plugged some weird device into the socket, which makes the power go out in our house. So next time he can just blame it on the weather, perhaps. All right. So thanks very much for that, Zainab. And in addition to all these, obviously the climate stuff, there's the simple fact that there's more and more IoT devices on the grid. So could you speak to a little bit about how these devices are impacting grid operations and real-time decision making, from your experience?
Sure, Hamish. And I think we'll all remember that we should just blame your son for the next global power outage. So yeah, there's if you look at all the renewables, I think probably most of the people on this call know that the model of renewables is really different than the model of traditional electrical grids. So you used to have a big power plant. There's a gas plant, an oil plant, a coal plant, and that's where your power came from. And maybe you had a few of those, and you had some substations, some transformers, and the delivery system. And now what you have are both industrial scale renewables that are on the grid. So you'll have your solar farm, your wind farm, maybe a geothermal implementation. In the future, you'll see small modular nuclear reactors floating around, not literally floating, but obviously at different places on the grid. But more importantly, you have rooftop solar, and you have people putting a single wind turbine in their backyard. You have people with battery storage on the grid. We're starting to see the advent of people's cars being used as batteries, right? That's coming forward. So you've got all these devices, and they're incredibly complex in terms of their interaction with the grid. And also you have often, if not managed right, misaligned objectives between the people operating those assets and the power grid. Now, hopefully your pricing model helps to make sure that people want to bring their batteries online the same time you want the battery power, that they're storing their solar power the same time you don't want it, and that sorts of things. But it creates a tremendous amount of complexity for grid operators to deal with. And they have, many of those levers they don't control. So, if I've got solar on my house and batteries, I don't, the grid operator doesn't control when my solar comes online, when my batteries come online. Now, there are grid operators who are making deals with people to say, you know, I want to control when your batteries are kicking in, when your solar is kicking in. I want to control your smart thermostat to raise the temperature or lower the temperature at certain times, and I'll pay you for the privilege of that. But all that is tremendous complexity when you start talking about a control system, and you can't possibly operate it the way we did in the past, where an individual operator is going, okay, let's make this, you know, we'll raise the amount of power from this facility, we'll lower the amount of power from this facility, we'll adjust this, and the grid's great. So all that complexity requires that we trust the automation of the control system, and the grid operator is pretty much just watching this happen, maybe making some adjustments. You know, maybe they need to bring a gas-fired power plant online. They need to, or they need to release some power from a dam, something like that. But most of this is going to be done in automated fashion with the operators just watching to make sure that this is under control. And while this is not so much about real-time control, I have to mention one of the big issues here as well is cybersecurity. You're bringing out all of these devices that are managed by individuals. You know, if I've got solar on my roof, that solar is now connected to my home network. And do I have a password on my network? Is it a strong password? Can anybody just hack in and find a backdoor into the grid through my home network? So not only do you have the complexity of all the devices, the need to automate it, but you have the risk of bad actors getting into that system through all these consumer grade devices.
Mm-hmm. Yeah, no, important point. I think we're all aware of those risks, and they're certainly only going to get bigger over time, I expect. All right, thanks for that, Anne. Simon, could you give us your perspective on some of the barriers to implementing real-time analytics, you know, from your experience?
Yeah, I'll just sort of first split this down into, you know, part of this is to do with the scale, so both the number and the physical scale of devices that are joining the grid. So, you know, as Anne said, people now have multiple devices. They're having complicated interactions with other grid providers at random times that aren't necessarily controllable. But all of those devices also, from my perspective as a database person, generate different types and shapes, if you like, of data. So some might look like document data, some might look like geospatial, others might look like traditional time series, just, you know, a series of classic temperature humidity readings. And also you might then be storing some of this as sort of vectorized data for AI models. So there's a lot of complexity that goes with that as well, especially as getting the full value of all of these devices quite often means combining all of these different types of data in one thing. And that's traditionally been a bit of a problem because data stores specialize in doing one thing or the other, or maybe a couple of them. And then you have to build glue and systems logic to link them together. And also the sheer scale of the data that all of these things generate mean that we as people have trouble understanding this, maybe without the help of AI, but also without the help of, you know, you can give me a source of real-time data, but it's just a fire hose, and the value of individual bits of that is very low until you can do a near real-time aggregation on that data and like step away from it a minute and show me the wider picture. So that's sort of, what are the barriers? I think it's partly that aggregation thing and combining different types of data. Also, the speed of the data coming in means that you need to make it queryable in a data store or something else very, very quickly to get sense of it in order to make that real-time loop a loop. You know, you actually take action based on these things. And then going back to something that Zainab said about, you know, sometimes you have to optimize existing things. Some things are there and they're not going to change because there's regulatory reasons, but there's more complicated pressures on them now. So billing, for example, as Anne said, you know, now might involve a provider sending me a check for something and then me being charged for something else. So some of the barriers are related to that and having to accept that you probably have to start duplicating data from one place to another to enable these things. Yeah, so that's
okay, fantastic. Thanks very much. Yeah, no, perfect. And because you were great segue into the next topic, because I know Jürgen wants to now talk about how energy infrastructure companies can best deal with some of those different types of data. So Jürgen, could you speak specifically, and perhaps also just explain to anybody who may not be familiar with the terminology, how do these infrastructure companies best deal with cold, warm, and hot data, and how do you manage performance and cost optimally? Before you start, I just want to point out that we're already halfway through, so if you can go through reasonably quickly, that would really help, because we want to make sure we get to some questions at the end. All right, thanks very much. Paul, can you bring up the slides again, please? Great, thanks.
Excellent. Then we just directly jump to a good use case. We mentioned already pumped hydro to stabilize the grid. I mean, the Valley Verganten Instruments has the headquarters, has a lot of hydropower plants. In the past, they pumped up the water in the night. Now they do it during the day because they have so much PV in the grid and wind. And in that particular use case, what you see here, we have a lot of gensets creating more than 1.8 billion values per day. And this data backend has to record the data for two different type of customers, internal customers. The one, they have to provide that they are actually running the engines when they get paid to pump it up. So for validation, they have to provide that data for multiple years. And others who want to have preventive maintenance output from that and do long-term analysis. So both of these people have different requests. The one needed instant, the other needed for decades. And here we run still on some use cases of this file-based, and then they can query through the local controller and get all the data. But you have to have here a very good access structure from cold, warm, and hot. Now, what is cold? Cold is what you hardly touch, but when you need it, it's acceptable that it takes a little bit until it's available. Warm is there with raw data, what coming in, and hot is you need that instant. It's pre-aggregated data. So in this example, hydropower use case, you really have the last year hot available. Then everything what is longer than a year is on a different database, which is imported then into streams, and then it's available for analysis or export. And now we come to the smart grid, where we have multiple players generating, producing. So I would like to go for the next slide. I would like to show you the smart grid use case from the University of Cyprus, where we have 10 hertz data of PV and so on. And there it's really that you have to measure everything at the same time, very synchronized, and take decisions, if you're out of the frequency. And one of the next slide, we plot here the frequency of a month in February, which you can play. There we easily see how the people then have to control that this grid stabilizes there, and that you have the ability to react instantly. And what is here really important, that you have on these decentralized systems everything perfectly in terms of time. So you have to timestamp everything accurately. You have dedicated watches and time synchronized for that in order to be able to meet the demand. And then you can control the system when you get the signal to reduce the power or switch on a battery and so on. So this is in a nutshell what I wanted to show here, to stay in the frequency of 50 hertz plus minus, and doing that real time.
Okay, fantastic. Thank you for that. And I know we also actually, this is maybe a good time to ask this. We have a poll. Paul, could you bring up the poll quickly, please? Exactly. So maybe people in the audience can give us their view on this in terms of what they find most important when it comes to real-time data. So please, if you can just provide us with your answers. And while Jürgen now talks about the next topic, then we'll come back to that in a minute and see what the results were. So Jürgen, perhaps you can just talk a bit more about what are the best ways to make real-time decisions then for energy generation systems, especially when it comes to the edge, and I think there are 3 analytics topics you want to cover in particular.
Yeah, well, this has different dimensions, right? You have the automated control and also market-based optimizations, and then you have also local optimization to keep everything in equilibrium. So we have the same generation and demand. And different stakeholders want to watch, but also want to help you in controlling or give you price signals. And for that, you really need open interfaces. And I prepared here a slide for that on the connectivity side. The next one, this is not the one with the frequency. It's the last one, where we really see that you have all the smart edge devices, which also have open interfaces, so people can integrate, read from there into their own asset, into their local database. But then you want to stream it to your PC, to your server, and access it with MATLAB, Python, and so on. And on the other side, you want to have long-term storage with a cloud-based backend where you use CreateDB and so on, and real-time enrichment to be able to have here decades of data that people train and run their models and also validate. And I think when you have all that systems on the edge, you want to have closed loop, but on the cloud, you also want to understand, why did it happen? So you need also the historic data, so you see the issues. And for that, it really helps that you have decades of data. We see here 8 years of solar and temperature data of an asset in Arizona, that you really can derive from here any trends and to try to cover the holy grail of preventive maintenance, which everybody wants to tackle. But you also should start to measure accurately without any averaging the raw data, so you can really later on zoom into the things quite well based on your question, what you want to analyze.
Okay, fantastic. Thank you for that, Jürgen. Paul, could you bring up the poll results for us, just so we see what people answered? So 57% synchronized data, 34% high resolution data, and 9% resolution. Jürgen, anybody else? Is that kind of what you expected, or is that surprising at all?
I think it's covering right well the things. We need fast data and synchronized data. It depends a little bit on the use case. I mean, it's obviously not helpful to measure the temperature 1,000 times per second, because there you don't need it. But it's obviously helpful to measure any vibration in combination with electrical signals. Right. And as we are moving in, or we are in an electrical grid transition, everything will be more electric, so you need fast synchronized data. And the kilohertz sampling quite helps. You don't want to store that for decades, but you have to have it available for the last 7 days, 30 days to take your conclusions and then put it somewhere on a cold storage. But synchronized is mandatory, otherwise you're off. That doesn't help at all.
Yeah. All right, great. Thanks for that. So Simon, do you have a use case in mind where you've seen an energy company have a success on a project that uses real-time analytics to optimize grid performance?
Yeah, so I could sort of offer a couple. So I've got direct experience of a few years ago working for a company where we built a proprietary mesh network and basically enabled a bunch of sensors in hotel rooms, so the thermostat and a door sensor and a PIR sensor and a couple of others. And had them send data to gateways, and then gateways would send data to the cloud. And the point was that you could, in theory, figure out when people were actually using their hotel rooms and combine that data with energy pricing data to sort of trade the hotel in the market as something that could be, obviously it can't generate any energy, but it can shed a bunch of load by deferring some aircon decisions. There's lots of interesting analytics around that, but you obviously don't just go, aircon to like however many degrees, and it just happens. There's a ramp time for that, and so forth. That my learning from that was ultimately that try to avoid inventing your own protocols, because hardware's expensive. So other people have already talked about using more standard solutions. And then more recently, where I work now, we have a number of customers that are having success with projects. So just briefly, we've worked with ABB on a smart charging solution for EVs, but fleets of EVs. So, bus companies and folks that go out and collect the trash, where you've got another sort of consumer level where somebody's interested in the performance of the fleet, as well as the performance of the individual vehicle, chargers, availability, and so forth. And these things have to be available, because if you've got a scheduled bus service, you need a bus that has enough power to go out and do it. And then I'll let Jürgen talk about the other case because, as Jürgen's mentioned a couple of times, they do use CrateDB at Gantner, so he's more the expert than I am here.
Okay, so we'll come back to that in a second. Thanks for that, Simon. I want to just quickly touch on the investment perspective with Zainab, because obviously her company tracks that side of things. What are some of the areas that you're seeing that are gaining traction with investors in relation to grid enhancing technologies?
Yeah, so we've definitely seen quite a bit of growth in this sector over the past couple of years. So just last year, we tracked around over $500 million invested in this sector, particularly in energy networks and grid enhancing technologies. And they covered quite a broad range. So these include things like advanced conductors, satellite imagery and vegetation management, dynamic line rating, and others. But maybe I was just thinking of calling out a few companies that particularly stood out. Mm-hmm. And so Ampersand and Ionate are both companies advancing smart transformers. Ampersand is doing solid state transformers. They raised around 12 million in seed funding last year. Ionate just raised around 17 million in their Series A round in February. And then today, DG Matrix raised around 20 million to advance their solid state transformer solution. So we're definitely seeing quite a bit of traction in this area. Another company that I want to call out is TS Conductors, and they raised around 60 million in their Series A round last year. And they're a really interesting company because they are using their kind of transmission conductors that are integrated with carbon fiber components. So there is this component of real-time monitoring that they're able to integrate into their system, and they can provide better feedback on things like sag, temperature, and operations. And they're a little bit more of a hardware-based company. But then there are other companies a little bit more focused on sensors, and these are things like dynamic line rating. And I think dynamic line rating is really interesting to talk about, especially when we're thinking about things like weather conditions and temperature fluctuations. And essentially, these are technologies that can identify potential increases in capacity. And they essentially, assess the weather, and they assess wind speeds. And I've seen, statistics that they can potentially increase capacity up to 40% just using, some of the existing structures already. So I think these types of companies are really interesting, and Line Vision and Heimdall Power are really great examples. And then there are a number of other, software-focused companies, companies using geospatial analysis, companies using satellite imagery. So AI Dash is another company that raised last year, and they have a pretty exhaustive vegetation management system. And then there are a range of other technologies, but I think I can save some of them for the later part of this webinar.
Okay, all right. Thanks very much, Zainab. And Anne, could you, I want to finish off before we get to the questions by talking about kind of how the future's looking from all your perspectives. But before we do that, Anne, could you just give maybe one example of a success in terms of real-time decision-making that stood out really from your time at the DOE? I think you're muted, Anne.
Sorry about that. I coughed earlier and muted myself, so I would interrupt y'all, and then I forgot. So yes, there are a lot of examples of really great real-time decision-making at DOE, specifically around grid management, and I think or energy management in general. But I think the most interesting one is one I alluded to earlier, which really is that the work that we do around managing wind farms, because it's so fascinating, right? To get this whole collection of wind turbines out there, and to the average layperson, it looks like you're just running these wind turbines. You turn them on, you run them, and you turn them off. And in fact, once they're sited for maximum capacity, you're also constantly doing real-time adjustments as the wind shifts to ensure you're maximizing your power output from each of those wind turbines. So it's absolutely a fascinating exercise to watch a control system as those things move. But there's one more I'll mention, which is sort of future energy grid in terms of real-time controls and real-time decision making, and that is the NIF, which is where we do research, where DOE does research on fusion, and the real-time controls are associated with the NIF to ensure that the laser hits the target at the right time, down to microseconds, is just amazing. And that is going to translate over time into that kind of real-time decision-making in production, where you're seeing constant adjustments in the control system to keep a fusion reaction going in the long term. So that's something that we're going to be seeing in the future. But the technology that's developed that's going to do that has already been developed at Lawrence Livermore Lab.
Okay, fantastic. Thank you very much for that example, Anne. And sticking with you, because we're just going to move on to the final section now before we move to questions, because we're looking to the future. And one of the big debates around this is radio frequency spectrum. And there's a bit of a tension there between the government and the private sector regarding that spectrum. So could you just give us an insight into what is the current state of that debate, and what are the potential impacts for the future, and how do you think it's going to evolve?
Yeah, and I can really only speak to that in terms of the U.S., although I suspect the debates are similar elsewhere. But in the U.S., keep in mind that the private sector energy users or energy providers operate on a different spectrum than the public sector. On the public-private sector side, there's a lot of encroachment on their spectrum, which is a concern from the standpoint of interference. In the public sector, it's a much bigger problem, which is the FCC wants to sell the spectrum that is currently in use by the public sector grid operators and other folks in the public sector use that spectrum, including Department of Defense, NASA, FBI. A lot of people are using that spectrum to control real-time device control, primarily for IoT or IIoT devices. And so the challenge is we've just finished moving the public sector off the previous spectrum onto this spectrum, and now FCC wants to push them up to even higher spectrum. That's an expensive move, and it's a distraction for all those organizations when they're looking at being able to modernize their grid, being able to increase cybersecurity. They have to redirect to move off that spectrum to new spectrum. The sale process should provide the funds to do that move, but it's still an expensive and time-consuming effort. In addition, there are proposals being made by the FCC for spectrum sharing in that space, with the idea that the grid operators could share the same spectrum as other sources, potentially mobile sources. And that makes the grid operators incredibly nervous. They might be sharing spectrum with a source that could move into their area and potentially disrupt the grid. And that really should make all of us very nervous that we might be trying to share that spectrum with somebody who could interfere with grid operation. So it's a contentious process. Lots of debate within the government. I don't know how that's going to. Well, I can speculate that there's just going to be more push in the new administration to privatize that spectrum. And probably with less regard to the challenges that the government is facing.
Okay, all right. Thank you for that, Anne. So Jürgen, let's get into the weeds again. What do you see as being the major needs for the smart grid of the future?
Well, I think we have here two different things. The first is what you have to have in place in terms of hardware, in terms of systems and backends. And the other one is, are you using the data, and for what are you using the data? And you have to answer both at the beginning. You should monitor what you need, but you should not monitor what you never analyze. So a lot of there is data there and stored, which is not helpful, especially when it is not normalized, when the meta information is wrong. So these are things. But coming back to the what to put in place, I mean, you need your components like edge computing, where you have all the sensors there, where you get all the data sources, everything is centrally stored. Then you put that into the data streaming backend element like Apache Kafka, put their real-time time series databases like create there, so you have efficient storage and fast access, which is, I think, very important. And once you don't need all that data, you put it to a data lake and compress it. So these are the elements. And nowadays, when we have also, international relations going up and down and changing very quickly, it's also important that this technology stack, hardware, software, backend, and hosting and security, that you have the full stack under control, so that there is no layer in between which you suddenly cannot use, and then you're stuck. So we have here our own security network. We have the Linux, even the real-time Linux under control, so we can build that up so you're resilient for that. And once you have the data, you should work with it. So you really want to have, once the data comes in, instant detection and gives you optimization potential. Maybe you run multiple models in parallel. I think that's also quite important, that you see different scenarios. You just trust one model, you run them in parallel and take the best out of it. One example could be, what kind of operation mode should I put on my battery? Is it just peak shaving, or is it also frequency control, and so on? And the other thing is, once you have all that data coming in, you should also do pattern matching and also, learning from the past, so that you avoid price decays, what you have in the past, and so on. And that's really the point, that you have the three important components. You have the edge hardware, you have the data streaming, and then in the cloud where you can run the models. I think that helps. So these are the three things which should be in place. And I think most of the technologies have established that.
Okay, fantastic. Thanks very much. And thank you also for providing me with my highlight standout quote of the day, which is, don't monitor things which will never be analyzed. I'm going to be discussing exactly that with my wife later on. Fantastic. I love it. All right. Thanks very much, Jürgen. Zainab, I'd like you to finish your thought about the investment perspective, in terms of how you told us a little bit about what's hot right now. How do you see things evolving from an investment perspective?
Yeah, and I think it's really interesting because when we're looking at the landscape of investments, in previous years, we've seen quite a bit of money going specifically into software tools and sensors. And I do think that trend is going to continue moving forward. But what's interesting now is there's this added hardware component. So previously, when we'd be talking to investors, there'd be concerns about like only selling hardware to utilities or not finding a strong enough customer pipeline. But now we're seeing that there's quite a number of hardware tools that can branch out to quite a few different customers, industries. And if they're also showing strong relationships with utilities, how that can scale forward. So there's a little bit more interest in this hardware space. And I think that will be one trend to look forward to. And then Anne mentioned a really good point about the fusion industry. And I think this is really interesting, just to keep an eye out on parallel industries that are commercializing. Even on the transmission side, we're seeing that there's investments going into companies that are advancing high temperature superconductors for grid transmission. And that's a really interesting result out of specifically a lot of advancements that haven't been made in the fusion industry. So keeping an eye out on what are the future trends moving forward, I think will be really interesting for us.
Fantastic. All right. Thank you very much, Zainab. And we're going to give the final word will go to our audience with a couple of their questions. But before that, Simon, could you just give us your insight into how you think the technology is going to continue to shape the future of smarter, more resilient energy grids?
Yeah, I think a couple of things picking up on what other people have said as well.
Yeah.
And was talking about, we need to maximize things like wind turbines and our existing investment in renewables, as well as double down on that. I just quickly checked what's called the carbon intensity of my electricity right now here in the middle of England, and me being on this webinar is currently brought to you by 73% natural gas generated electricity. I live in a really windy country. That's like a problem. So how can technology help with that? Well, we can't put more turbines up, but we can provide more analysis on things like where should those go and how are they optimized on a minute by minute or faster level to get the most out of them. I think also, to pick up on something that Zainab was saying, there's more investment in hardware, and I would expect hardware to get when we talk about scale and hardware, quite often I'm more interested in the tiny, if you see all the things behind me, and the tiny things get very cheap, which means lots of people have them and lots of people can understand and have, when they've got a consumer interface, deal with them. And that generates huge demands for data and also expectations of micro control of people's own behavior on the grid. And also, again, to go back to what Anne was saying about spectrum, all of this stuff, when it gets into the hands of the consumer, is going to be flying around over, essentially Wi-Fi type spectrum, broadband, maybe some sort of 5G phone stuff. So demands on the mobile carriers and adjacent industries as well. In terms of where I sit as the database company, then I would expect us to have to continue to deal with increasing volumes of data, but also have a little bit more introspection about well, okay, what's our energy usage and what's our storage requirements? And, compute footprint and storage footprint are something that we've been working on. And I think that will be continuously more in mind for people, especially if they're deploying hybrid solutions like Jürgen was talking about, where some of this stuff's on the edge and some of it's in a cloud. That edge stuff has to be managed a lot more. So it needs to be really efficient. But yeah, I'm just mindful of time. So that's where I'll leave that.
Yeah. That's fantastic, Simon. Thank you very much. And that does leave us, fortunately, a couple of minutes to get through a couple of questions. So thank you for allowing us to do that. So first one is directed to nobody in particular, whoever has some insight. How much are power purchase agreements increasing or decreasing with the increased power demand across EV charging, energy storage, renewables, data centers, etc.? Does anybody have any insight into that, power purchase agreements?
I could comment on that a little bit.
Yeah.
So the PPAs are currently, I can speak for Germany, they have an imbalance. For example, if you want to sign a new PPA now in Germany for the next 5 years, you need roughly 91 euro per megawatt hour, but you get on the wholesale market only 50. So there's a big gap. So people have to look for PPA partners which give them roughly more than you just get on the wholesale market, because time of use is not optimized. We are changing the energy infrastructure, and therefore you have to find out all the different options, maybe during the day, how you should flow the energy in the right direction, maybe charge at the right time, do peak shifting and all that stuff. And for that you need real-time data, and I think it's impacting there. Investors are realizing that it's not a straight line as you want to have it in the Excel for 5 years. You have to optimize continuously, and batteries, electrolyzers, but also other types of consumers are a big help in doing that. But it has to be done smart. There will be a fast change, even faster than what we have seen. This is what we see from our data acquisition world.
Mm-hmm. Okay, brilliant. Thank you very much. One more from David Kyle. With recent dramatic changes in international relations, very diplomatically put, unexpected technology restrictions and tariffs, is moving off cloud services to self-hosting a viable strategy? Anybody got a view on that?
Well, I mean, I would guess my question would be, why would it matter? I mean, unless they're worried that, say, they're outside the United States, their cloud provider is in the United States, mm-hmm. There are places in their own geography they can almost certainly find a cloud provider that will support them. I sort of think if you want to be on premise, that's fine. It all depends on your application. So I'm not sure there's enough information really to truly answer the question. Okay. But I think that fundamentally, you can find if you want to use cloud service, you can provide in most places, you can provide a provider who's got a data center in your country with a commitment to keep it in your country, if that's the concern.
Okay. Yeah, probably a bit more context needed. Anybody else got a general thought on that before we close?
Just as biases, I work for a database that can be deployed hybrid on the edge and in the cloud. Sometimes it's going to depend on your business process. Some things, like if you're operating a factory and the internet goes down, then you don't want to be making routing decisions about where things go along warehouse conveyors in the internet anyway. So you might be self-hosting, but also I think you have to consider the sort of trade-off with the economic decisions. By going to the cloud, you still need technical people to manage all of these services, but taking it on yourself is a whole nother grade of, now you're into hardware provisioning and replacement and so on. And are you able to buy those things at scale enough to compete with the cloud providers? No, but if it makes sense to take on that cost, then great, but have a good think about it before you do.
All right, perfect. Thank you very much, Simon. I'm afraid we're out of time. If we didn't get to your question, we will get to it by email after the event. So thank you. Thanks to our panelists for your insights and your knowledge. Thank you again to the sponsors of this session, CrateDB. Your support ensures we have all of this great content to share, so we're really grateful. And also, of course, for all of our speakers participating. Thanks to you, our audience, for listening and for your great questions. And it's now time to move into today's next session, which is cybersecurity in the energy industry, protecting critical infrastructure in a connected era, sponsored today by Key Factor. So thank you very much. I will see you at the next event in May. Enjoy the rest of your day.